main idea was trying to understand what sets the patterns of ocean warming in the past, what sets the patterns of ocean warming in the future. And for that, we kind of relied on a link between anthropogenic carbon and heat. And so the maps that you see here are basically observations starting from 1971 to 2010 of ocean warming. And you can see patterns are non-uniform. Places are warming faster or slower than other places, and not all places are warming. If we go into the future, then the maps are becoming yellower, so they're becoming warmer. The ocean is taking up more heat, it's storing more heat. But again, this pattern is non-uniform. So we've been trying to understand how the ocean circulation has been setting those patterns in the past, and how they'll change those patterns in the future, and are those patterns actually governed by the same mechanisms over time. Okay, give you a bit of an outline. So I'm going to start by talking about heat and carbon uptake in very kind of broad terms, and the mechanism setting patterns of warming. And so then the core of the talk will be kind of distinguishing between what I'm going to call added or redistributed heat patterns. Added mean you can think about it as kind of a bit of a passive type tracer. So we put CO2 into the atmosphere. There's an excess energy. That excess energy is being absorbed by the ocean for the most part, and kind of stored passively by the background ocean circulation. Then the redistribution will be, in our case, in our definition, how the changing ocean circulation is setting those patterns. And what we'll see is that there is a big difference between anthropogenic carbon and heat. And both, in terms of their regional distribution, but not necessarily in terms of their global uptake. So I'll show that there is a link between global heat uptake and global carbon uptake. And so we're going to use those kind of different links between heat and carbon, both globally and regionally, to try to infer how the ocean circulation has set the past ocean warmings and the past patterns of ocean warming, and how they'll change that in the future. So this is how we're going to basically disentangle how the ocean circulation has changed and how that has affected patterns of ocean warming. And so I'll give you a few thoughts or random comments, I guess, at the end, trying to claim that it's possible that future trends are more predictable as the warming trends emerge. But of course, it's going to be based on coarse resolution climate models. So I'll have to take all of that with a pinch of salt. But also that if that's true, or if everything I'm saying is true, or at least partially true, there might be a possibility to try to find emerging constraints for predicting future patterns of ocean warming. Okay, so I don't know how it works, but I'm quite happy to be interrupted if people have a question in the middle or whatever. Also, that makes me feel like I'm not just talking to my computer. So feel free to interrupt. Then if you interrupt too much, I'll tell you. But feel free to interject if there is clarification that you need or anything else. Okay. So I'm going to start with a reconstruction of carbon uptake, so from Katiwala et al. So here what we see is basically, as we all know, we've been putting CO2 into the atmosphere. Some of that remains in the atmosphere, but a big chunk of that is being absorbed, and it's being absorbed by the ocean. If we look at the same kind of reconstruction for ocean warming, again, the ocean has been taking up a lot of heat. So again, if we go back in time, basically over the 20th century all the way to present, about 90% of the excess energy that we put in the climate system is being absorbed by the ocean. And those are the trends that we're seeing here over time, especially in the upper 2,000 meters of the ocean. So we put CO2 into the atmosphere or additional greenhouse gases. A large chunk of that is being absorbed by the ocean. And so we see both global heat and carbon uptake over time. But again, even though the ocean is absorbing heat and carbon, it doesn't do that uniformly. So here on the map here at the top, those are observed patterns or trends in observation in the upper 2,000 meters of the ocean. And so what you can see is something pretty obvious, is that some places are warming, say the Atlantic Ocean, but not the subpolar gyre, for example, that is cooling. If you look at the Pacific, same thing. We see many regions that are cooling, but we see broad range of warming over the Southern Ocean. So the ocean is taking up heat, It doesn't take up heat in, equally everywhere, and it also does not store it everywhere in the same fashion. And we'll see that the ocean is actually playing a pretty big role in that. Of course, as you all know, because it's a sea level seminar, if I warm the ocean, water will expand and sea level will rise. And so as a consequence, thermosteric sea level rise will also not be uniform because the patterns of warming are non-uniform. And so again, this is what we see in the map down here at the bottom over almost the same period of time, minus about a decade. But again, some places see a higher thermosteric sea level rise than other places where actually they see a decrease in their trends. Okay, so basic equation to actually describe how those patterns are set. So at every single point in the ocean, the change in temperature anomaly, T prime, for a given forcing will be different, again, at every point. If I integrate, a full equation, the global heat uptake will only depend on the forcing, not the redistribution. But again, at every point, there are a bunch of other terms, and those are the other terms that we have in the equation. This first bit over here within the divergence is going to be advection. So we advecting temperature anomaly, T prime, with the background velocity. So that will be kind of the pre-industrial velocity. And then again, as the climate is changing, either from natural variability or from the anthropogenic forcing, the ocean circulation is also changing. So that's the V prime that you're seeing here. It's going to be the ocean circulation that is adjusting to different forcing. And so that changing ocean circulation is going to advect both the background temperature that was there before we've added some forcing, and also the anomalous temperature. And of course, the ocean mixes stuff around, right? Both horizontally or in terms of isopycnal mixing and diapycnal mixing. So all those terms over here are just moving heat around. They're just redistributing it. And this term F prime is what's adding the heat into the ocean. Okay, so one term at a time for the advection, because this is what we're going to concentrate on. The first term, you can think about it again as the redistribution of the added heat, the added anomaly, by the time mean velocity. You can think about kind of the meridional overturning circulation as a function of depth and latitude. And you can think that heat might be taken up in the North Atlantic and kind of be advected passively by this ocean circulation. Same thing in the Southern Ocean. And you can think about it as this added heat will not change the circulation, just being added passively and being moved around by the background circulation, which is in our case, the pre-industrial circulation. The two additional terms are the changing temperature or the changing heat content due to the changing ocean circulation. So that's the redistribution by this kind of time-dependent changing circulation. So now the bad news about this component, it's usually pretty hard to infer. So, and it's not a criticism of models, by the way, it's hard to actually model the changing ocean circulation because it depends on many things. And this is just an example to actually just illustrate that. It's a very nice paper by Alicia Karspek in 2017, looking at the reanalysis, at different reanalysis products. So again, observations plus models together of the overturning circulation. So the change in overturning circulation over part of the historical record at 26 north and 45 north. And each one of those lines is a different reanalysis product. And I don't need to say much here, is that they're all over the place, right? They don't have the same trends. Some of them see a decrease, others see an increase at 45 north, for example. The variability is quite all over the place. So it's very difficult to actually infer how the ocean circulation has changed. And so just something to keep in mind as we move forward. Okay, so I show you that equation, and of course there is a reason for that, is we're going to use it to try to disentangle how much of those patterns in the past, so that's for the observations that we've seen before, and in the future are set by the background circulation. So you're just adding anomalous heat into the climate system and it's being passively taken up by the ocean, versus how much is due to the changing ocean circulation. And the one thing that I want you to see here is that in the past and in the future, the patterns are quite different. There's a fair bit of I don't know if it's background or if it's somebody who's not muted. All right, it's quieter now. Thanks. Okay, so in the past, again, we can see many regions where we see coolings, we see areas of cooling, and in the future, everything looks warmer, but again, non-uniformly. And so are the same mechanism dominating in the past and in the future? And if so, what are they? And if not, again, what are those patterns? So I'm going to start by kind of telling you our recipe, the way we kind of disentangle the role of the ocean circulation in those patterns. The first thing we did was to find a link between heat and carbon. And the first one was global. So in this plot, I'm showing global ocean heat content. So this is going to be in a vertical axis versus carbon content of the ocean in both instances, in observations and in different models. So the observation is the blue line, and the red lines are different simulations. So what you see here is, overall, there seems to be a pretty tight linear relationship between global heat uptake and global carbon uptake. That relationship also seems to be kind of relatively independent of the model and the simulations that you're taking. So that will be the first thing that we're going to use. The second thing we're going to use is model similarities between heat and carbon uptake if we were to fix ocean currents. So this is what heat and carbon, so that will be heat uptake and carbon uptake in a simulation in which CO2 is doubled. So it's a simulation by Mike Winton and colleague, kind of almost 10 years old, but it's a fantastic simulation. Then what they did is they took the same climate simulation in which they increased CO2 and rerun it, but now they fixed the ocean currents. So now you don't have a V prime anymore. You only have a V bar from the pre-industrial circulation. This is what you get. This is the pattern of heat uptake. So now it looks very different than if you were letting the ocean circulation kind of adjust to that warming. But if you look at the carbon uptake, then it doesn't look very different than its counterpart when the climate system was allowed to, when the ocean was allowed to respond. But most importantly, now the pattern of carbon uptake look the same as the heat uptake under a fixed circulation. So we're going to use that similarity between heat and carbon under this kind of fixed circulation experiments to move forward. Okay, so that's just the recipe. Now I'm going to take it, I'm going to take the first step and then a second step to show you how to decompose that. So I'm going to pause for a second if there are any questions or comments. Okay, I'll take silence as no. So I'm going to start with again, kind of going back to this plot of heat uptake versus carbon uptake and this kind of linear relationship between the two. So while the linear relationship was a bit of a surprise, it was a bit of an hindsight 2020, in the sense that it kind of makes sense that it was linear, and I'll tell you a little bit why. First piece of evidence was we already know that surface temperature in the climate system is actually proportional and linearly proportional to cumulative carbon emission. So it has been shown already for about 10 years. And some of the arguments that were brought forward was, the ocean is responsible for that linear relationship, or at least in part responsible for that linear relationship. And so again, this is something that we see in all models. Again, the linear relation is not a set number, but again, that kind of linear relationship between how much the surface temperature is going to change versus how much carbon you emit has been shown before and explained before. So now, since we know that the ocean is taking up a huge chunk of the excess warming and the excess energy due to the amount of CO2 that we're putting into the climate system, and that the ocean is also a pretty big player in how much carbon is being absorbed, and rather than remaining in the atmosphere, makes sense that the two will be linked. So what again, just to show you exactly the same plot, but in a different version. So here we're plotting this ratio between the global heat uptake to carbon uptake from different CMIP5 models. So that will be the historical simulations. So the two dots that you see down here are a couple of models that unfortunately were cooling over the historical period. So I would personally discard them, but we put them out there just for the sake of completeness. But otherwise, the CMIP5 model gives us about something that's about 4 times 10 to the 7 or 5 times 10 to the 7 joule per mole, with some kind of a spread, but nothing big. If you go to an RCP 8.5 scenario, those same simulation, this kind of ratio between heat and carbon uptake is not vastly different, right? The spread is also kind of fairly similar. The mean is moving up a bit, again, because those models now are not cooling anymore, but not a big change. Those are observations or reconstruction to some extent. So again, kind of within the ensemble mean. And that's ESM2M, so that's the Earth system model that I told you about before, again, kind of within the range. And this is an ocean-only model that we used as well to kind of, again, do some intermodal comparison. Overall, kind of a tight spread between, I see things in the chat. Is that for me or no, Craig? Sorry, I can't see everything. I'll wait patiently, but basically overall, this kind of ratio seems to be pretty similar between different simulations and different models. So any questions?
We have a question in the chat, a couple of questions in the chat. One from Natasha. How confident are you in carbon uptake and storage from observations?
Yeah, great question. Yeah, thanks for that. Yeah, it's a great question. So it's a reconstruction, obviously. So we used, in this plot, we used Team de Vries reconstruction. So again, they use an inversion to estimate anthropogenic carbon. We did the same with the Katiwala reconstruction. There are definitely errors. I mean, I'll never claim that observations are clean, nor that models are. But it gives us, we use two different products and we get the same answer. So there is definitely spread in that, for sure.
Yeah, I'm sorry I missed these questions. We've got a couple. I was too engrossed in the talk. Yeah. So we've got a message from Gavin. He's asking, have the CMIP runs been adjusted for climate drift?
Okay, so in those cases, we didn't. We used them as is in those dots over here. We literally took every Earth system model that was available because we needed to have a fully coupled, carbon cycle.
And sorry, just blast through this.
So no, go for it. It's much better. It's much better than talking to myself.
Yeah. It can be particularly hard when you're just talking into a computer, I think. Yeah. But so we've got a question from Viviani. Can you explain the geographic differences in ocean heat uptake, in particular why the Atlantic Ocean is warming more than Pacific?
Yeah. So that's going to be the talk. That's going to be the talk. Yeah. It's coming.
And then Gavin says, "Oh, that'll be a large part of the spread then."
Indeed. Yes.
Okay.
Yeah, that's correct, and that's why I'm not all that fussed about this. Here it was really kind of showing some of the basics, but we're only looking at kind of the global uptake anomalies from pre-industrial. Okay, cool. Okay, so what we're trying to do is trying to understand that number basically. Okay, and it's a back of the envelope, so take that with a pinch of salt. I'm not saying that our scaling is correct, but it was to give us a rough order of magnitude for what that ratio between heat and carbon uptake is. Gonna take our favorite climate model, which is a box model, where you assume you have an atmosphere, an ocean. This is our simple climate model. N is the relative imbalance at the top of the atmosphere. And of course, as we said before, we're putting CO2 into the atmosphere. I'm only gonna concentrate on CO2 here, simply because of the experiments we've been running. So putting CO2 into the atmosphere, again, the atmosphere or the climate system will adjust to that. R is again gonna be the relative feedback. It's gonna assume that is basically linear and proportional to the surface temperature. And again, F is the forcing. If we assume that most of this kind of imbalance at the top of the atmosphere is being absorbed by the ocean, so we're gonna say that N is equal to the HDT, which is the rate of ocean heat uptake. We do a little math, nothing fancy. And we're also gonna assume that F, again, because I'm only looking at CO2, is gonna be basically the log of the partial pressure of CO2. And F naught is gonna be the magnitude of the radiative forcing to CO2. So if I take that equation, integrate it over time, over a certain amount of time, delta T, this is what I get. All right, so it's gonna depend on the radiative forcing of CO2, and of course, how much feedback or how much damping I get from the atmosphere on the surface. So now we know, again, it's a little bit of chemistry, and I'm not gonna go into that because I wanna talk about the ocean dynamics and the patterns, But again, just to first order, we can rewrite the ocean PCO2, so the partial pressure of CO2 in the ocean, as a function of the atmospheric PCO2 and the buffer factor, which is basically the ability of the ocean and based on its chemistry, its biogeochemistry, to take up carbon. And so I'll care about temperature, and again, a lot of biogeochemistry that I won't go into the detail, but also what we call the carbon inventory, kind of the basic storage of the ocean in terms of its carbon content. So a bit of mathematical manipulation, and we get alpha. And again, to remind you, alpha is the net ocean heat uptake divided by the net carbon uptake. And so H was basically my net ocean heat uptake, and I'm going to divide by the net carbon uptake, which again, I've estimated using this kind of little relationship between ocean PCO2, atmospheric CO2, buffer factor, and carbon inventory. This is the equation we get. We get R, which is the buffer factor, A, which is surface area because we've integrated over the ocean, F naught is the radiative forcing due to CO2, I naught is the carbon inventory, so basically the carbon storage, which is kind of, again, from the pre-industrial state, not from the changing state. Delta T is the amount of time that we're considering. And the second term over here depends, again, on climate sensitivity, the surface temperature, and how much carbon we put into the atmosphere. When we did a little scaling, this term actually doesn't matter all that much, or at least in terms of its magnitude. It matters to give us the linear relationship, but doesn't matter for the amplitude of it. And if you take any climate model, or at least any Earth system model that we picked so far, and you use those basic kind of coefficients, you would determine what alpha is, within 15 to 20%. And all those parameters are directly diagnosed from the Earth system model, so it's very easy. And they actually come pretty much from the pre-industrial state. So your background state seems to actually determine how much heat and carbon uptake you'll take overall, only based on the forcing that you're imposing and the background ocean circulation. So that was kind of our back of the envelope for why alpha is what it is. Depends on, again, the ocean state, both its carbon state, if you want, and its ocean stratification. But again, this is something you can diagnose from the model, so you don't need the scaling. It was more for us to understand what it was coming from. So now that we have that scaling, we're going to use the second part of the talk, which is this kind of similarity between heat and carbon. Okay, so I'm going back with that simulation from Winton and colleagues, in which they took an Earth system model at 1% CO2. This is what the coupled simulation gives us in terms of heat uptake. So again, this is the pattern of heat uptake. Now, in the second simulation, again, they do exactly the same thing. They put CO2 into the atmosphere, 1% CO2 per year, but now they're not letting the ocean circulation change. So in our equation down here, V prime is in existence now. But the climate system is still, doing its own business, but the ocean is not allowed to change its velocities, its resolved velocity. And that's the pattern of heat uptake that we're getting. So now look, now the subpolar gyre is actually warming, it's not cooling anymore. So already gives you a hint that the changing ocean circulation is responsible for the subpolar gyre cooling. You can calculate the residual, right, between the total storage on the left, the middle panel, which is the fixed circulation, and that gives me how changes in basically resolved advection, so changes in V prime, have been setting the patterns of ocean warming in that simulation. Cooling in a subpolar gyre, right? So cooling in, or at least kind of damping of the warming signal in the Pacific, same in the Indian Ocean, but, kind of additional warming in the tropical Atlantic, say, and at the entrance of the Atlantic basin in the Southern Ocean. So the ocean circulation has the changing ocean circulation or changing ocean advection has been pretty, important in setting up those patterns in that simulation. And as we said before, if we look in that Earth system model at what the carbon is doing, the carbon is giving us a very different picture. So first, the pattern of anthropogenic carbon in that simulation, in the full coupled simulation, looks very different than the heat. But then when they fix the ocean current, so that's kind of V prime is 0. Again, it's kind of passive or added storage. The pattern of anthropogenic carbon looks pretty much identical. There's almost no change. The correlation is more than 0.9. But it looks very similar to the pattern of added heat, right? So in which we fix the circulation. So again, added heat is very much like a passive tracer, like carbon. And again, just if we calculate the residual, the redistributed heat, the redistributed carbon, sorry, is pretty much negligible. So we're gonna use this kind of similarities, that if I have an Earth system model, it has anthropogenic carbon, that means I can use the pattern. And if I have that pattern, that means that I know what a pattern of added heat would look like. The one thing that I'm missing is, of course, a conversion of units, because this is in moles and this is in joules. So we need a link between those two patterns to actually convert the units if you want. And that's where the alpha that I talked about comes from, right? Because this is heat uptake to carbon uptake. So it's a conversion basically from carbon to heat. And so that's what we're gonna use to make our reconstruction. So within that simulation, because I have everything, right? So I can definitely see what the patterns look like. So we took the pattern of anthropogenic carbon in the Earth system model. So that's Cnt at every single point at every time, and multiply it by the heat to carbon uptake ratio, which I can diagnose from the model because I have it in a fully coupled simulation. And that gives me a pattern of added heat without having to run the fixed circulation experiment. So the patterns over here on the left is the pattern of added heat based on our estimate. So based on our little calculation over here. And this is what's simulated in the climate system, in the climate model, sorry, when they fixed the ocean currents. So again, does a pretty good job, right? It gets worse at high latitude. So the global mean error is about less than 10%, but it gets worse when you're near the ice, which kind of makes sense in regions where, again, you have a lot of ice formations here and there. So that's usually where our errors come about. But what's interesting is the patterns and the errors of that added heat are very comparable to estimates, using Green's function that some of us have done, in which we assume a constant ocean circulation. So widely different methods still gives us kind of the same basic picture of what the added heat should look like in general, but here we've relied heavily on the pattern of anthropogenic carbon. So now what I'm gonna do is I'm gonna use this recipe on a bunch of data. One is gonna be observations, and the other one is going to be Earth system model from the CIMIP 5 archive. So before I move on to actually describe the patterns, I'll see if there are any questions or comments. Okay, all right. So I just want to again highlight this is a prediction based on models and also let's say intuition for the most part and some quantitative analysis, but it's only it's only a reconstruction if you want, right? So it has errors. You have to take everything with a slight pinch of salt. We're only interested in the broad patterns, so kind of large scale patterns rather than local changes, because there are so many errors in so many places. But based on what we found as kind of a, or at least what we think is a useful relationship, we're going to try to split the observations into added heat, which is going to be due to the background circulation, due to an added kind of anthropogenic forcing. And the residual will be the redistribution, which is due to the changing ocean circulation. Okay, so let's start with the arms. So this is the patterns of ocean warming over here that I've shown you many times before, over 60 years. This is our reconstruction using anthropogenic carbon of what a pattern of added heat is, again, based on our prediction. So first thing to note is that they look different, right? Added heat and the real observations are quite different here. So the added heat tells us that, well, a lot of places in the Pacific should be warming, and most of the North Atlantic should be warming as well, but this is not what we see in the Alps. So the residual between those two will be what the changing ocean circulation has been doing to the patterns. And so now, so where you see shading, it's basically not statistically significant. So I would not, again, focus about those regions. But overall, what we see is that the redistribution, the changing ocean circulation, is responsible for the cooling in the subpolar gyre. So basically, V prime, if you want, in my equation, is responsible for the cooling in the subpolar gyre. It's also responsible for a large chunk of the warming over the kind of Gulf Stream region, so the mid-latitude, and also part of the Southern Ocean warming at the entrance of the Atlantic. So this indicates that the ocean circulation has been changing in the Atlantic, and has been setting a lot of those kind of amplified patterns of warming. And in the Pacific, again, kind of cooling trends in the redistribution have been dominating the observations. Over the entire Southern Ocean, so let me move in, so that's what I said here. For Indo-Pacific, again, so we have cooling of the subtropical gyres. So that's kind of those kind of two regions that we see in the obs, so dominated by the redistribution. Now for the Southern Ocean, if we look at the added heat, right, so it's pretty similar to the obs in the sense that they have a uniform band of warming, and that's been shown to be kind of, again, passive advection of excess warming by Kyle Armour and colleagues, a few years ago. But this kind of amplified warming at the entrance of the Atlantic and the Indian Ocean is not simply explained by just passive advection. There's a pretty big contribution of a changing ocean circulation there as well. So in addition to this kind of basic passive uptake in the Southern Ocean, that is a very powerful mechanism, there's still a change in ocean circulation at the entrance of the Indian Ocean and the Atlantic Ocean, causing a large redistribution. But overall, if I look at patterns of ocean warming in the past, over the historical period, they are pretty much dominated by redistribution, by the changing ocean circulation, and not so much by a passive heat uptake. Questions, comments, criticisms?
We have a question from Clara in the chat.
Sure.
Sorry, it's from earlier. So to what extent is the transit time distribution / Green's function well approximated by an inverse Gaussian?
Oh, that's a good question. Okay, so it's not, I would say, it's not too bad, but it's never perfect, right? Because those estimates are always tricky. The more transit tracer you have, the better your estimate would be. For our Green's function for heat and the Katiwala that we used the Green's function based on transient metrics. So it's kind of a different way. We didn't have to make that assumption of the inverse Gaussian. So that kind of helped us kind of move away from that. We literally kind of, it makes no assumption about the distribution itself. So we didn't need to make any inversion. That's a good question. Anything else?
Oh, we have a question from Gavin now.
Yeah.
In the model, you can calculate the uptake of a true passive tracer or something closer than C, i.e. CFCs.
Mm-hmm.
How different is that from what you get from C?
Yeah, that's a great question. And we checked into that because initially we thought that any passive tracer will do, and that will make our life quite easy because we all put passive tracer in every simulation, including with the FAFMIP experiments that we've been running. In the 3 models in which we had anthropogenic carbon and could do the simulation of like fixing the circulation, we did not find the same distribution for CFCs as we find for anthropogenic carbon. And the reason for that, again, we don't know if it's a coincidence or not. So I want to, again, kind of, give you a grain of salt with my explanation. We find that the kind of the buffer factor was important. So the chemistry of anthropogenic carbon and its sensitivity to temperature were important at giving us exactly the same patterns of added heat. But we didn't find that with CFCs because it doesn't have this kind of biogeochemistry or this kind of chemistry component to it. And that's why we never found the same distribution or as high correlation as added heat as we did for anthropogenic carbon. This is something that we're definitely pursuing, but there's a large chunk of chemistry in the paper that I definitely won't go into it. That's a great question. And still a puzzle for why carbon is so special because of its chemistry.
And we have another comment from Vivian. She's keen on understanding the Pacific Atlantic difference
So again, great question. So it's only a hypothesis here, right? Because it's an inference of an inference. So, but there's been quite a few papers talking about the Atlantic as a reduction in the overturning circulation. So large-scale advection from low latitude to high latitude. So that would be consistent with a cooling of the subpolar gyre and a warming and excess warming in the low latitude and mid latitude. Now, is it due to anthropogenic climate change or just wind-driven circulation? We have no idea. My guess, because of what the models are doing, I'm more inclined to say that over the 50s to 2000, it's likely due to natural variability. Second argument, it's not necessarily kind of a deep overturning, but it's also, the gyres, the boundary between the two gyres is also kind of quite sensitive to wind changes. So in general, if you have a change in one hemisphere, in the subtropical gyre, you'll have a change in a subpolar gyre as well, because again, simply Ekman transport will give you a mirror image. Of course, there is no overturning in the Pacific, and that's probably one of the reasons that there is a bit of a difference there. Some people have argued changes in, again, kind of spin up or wind-driven spin up of the gyres in the South Pacific. So there are quite a few hypotheses out there, but I think there's still a lot of work to be done in kind of pinning down those differences. So I hope I give you a hint, but there are definitely quite a few papers out there.
Thank you.
All good? Yeah, cool. All right, so now I'm gonna look at models. So still CMIP5 models during the historical period over the same trends. So at the top are the OBS that I showed you before, the direct measurements, direct measurements. That's the added heat that we've estimated. And that's the redistribution that is calculated as a residual. That's the CMIP5 ensemble mean kind of historical simulations. So what you can see is the ensemble mean is not greatly consistent with observations. And again, we can't ask for our models to do everything right. It's complicated, especially to get the historical period right. For example, on the ensemble mean, they showed that there is a warming of the subpolar gyre rather than a cooling that we see in the OBS. And so again, in our humble observation, it's probably due to the fact that those trends are due to natural variability and not necessarily kind of the force response that the models struggle to capture. But if you look at the added heat, based on our reconstruction, again, taking anthropogenic carbon, or coupling between heat and carbon together, actually the pattern of added heat in the CMIP5 and in the OBS has striking resemblance. So we're arguing that actually, in terms of passive, if you want, or added heat uptake, the climate models are doing a great job overall, but they don't do a great job at getting the redistribution. And again, it's harder to get the redistribution because it's a changing ocean circulation, and the models struggle with that part, especially if it's due to natural variability, which the pacing will always be off. And again, will penalize a lot of models when you look at the ensemble mean. But they still show a very strong redistribution signal, which still dominates a large chunk of the historical warming in the CMIP5 model, meaning, again, redistribution in the past was pretty dominant, even though the models don't necessarily do exactly what the OBS are doing, but they still do a pretty decent job. Okay, so that was for the past.
Sorry, yeah. Gavin is making a statement in the chat.
Okay.
Just to break things up, Gavin, is there any chance you'd like to unmute and?
Well, no real reason to unmute, but yeah, I mean, so the kind of going back to the previous point, which is related to this. So your argument is that the correlation of C and H uptake actually relies on a common nonlinearity in those two cases that is different to what you would see in a passive tracer.
Correct.
Right? And that nonlinearity is probably temperature mediated because that's that goes into the chemistry of the carbon and in presumably changes in stratification of heat.
Exactly. Yeah, bang on.
Okay. Okay. Thank you.
No problem. Okay, cool. Yeah, and again, you know, that we came up with a few arguments for why, but that definitely remains, you know, something to be explored much further than what we've done, and see if it's actually robust as well. Yeah, that's a great point. Okay, so now we're going to look into the future. So the past, you know, we had the ups. We know what the real deal is. In the future, we have models which we love very much, and so we're going to use them to try again to disentangle how much of the pattern is due to the background circulation and how much is due to the changing ocean circulation in those simulations. So again, a system model CMIP5 going into 2060 under an RPC 8.5 scenario. So our estimate of the added heat in those simulations, in those fully coupled simulations, in which we used, again, anthropogenic carbon and our ratio of global heat uptake to carbon uptake, this is what a pattern of added heat should look like. So now, unlike in EOBS or in CMIP5 historical period, they look very similar, right? So now it's not as completely, you know, off to say that to first order, it looks like into the future, the passive uptake of heat seems to be dominant. If we take the residual between, again, what the simulation are giving us, what our estimate of added heat is, that would be the redistribution. So like we've seen in the arms, right? We see kind of cooling in the subpolar gyre, excess warming in the tropics, both in the Atlantic and Pacific Ocean. And again, kind of cooling in part of the South Pacific and Indian Ocean. But now those patterns don't dominate the global patterns of heat uptake anymore into the future. They are dominated by the added heat. So overall, the redistribution is going to damp the signals in the mid-latitude and kind of amplify them in the tropics to some extent, but they're not dominating it anymore. So pretty different kind of picture that we have here. Again, you know, Matt and Alex have done kind of FAFMIP, you know, experiments showing that, you know, there's a large spread due to the redistribution, meaning that the models still struggle doing that into the future. So again, maybe this is all wrong, but this is what our coarse resolution climate models are telling us, that into the future, most patterns of heat uptake are dominated by added heat. Redistribution, even though it's happening and has a very characteristic pattern, has a weaker amplitude compared to the added heat, meaning the background ocean circulation is going to dictate how much heat storage we're going to see into the future, just based on just how much warming we're putting in. Okay, the resolution of that figure is pretty bad, but I hope you can still see it. So this is the correlation. This is the pattern correlation between, it's a pattern correlation between the total heat storage in the simulations since 1950 and the different components that I talked about. One is redistribution, so that's going to be the blue one. So correlation between total heat storage and redistribution and the pattern of redistribution. And the orange one is the correlation between the total heat storage and the added heat. Basically, what I'm trying to say is that if the correlation is high, here for the blue, that means that the patterns of heat storage are look mostly like the redistributed heat. And you can see that's what we see over here. It's close to 1. So the patterns of heat storage in the past were almost entirely explained by a pattern of redistributed heat, but that correlation decreases over time as we go into the future. On the other hand, the correlation between the total heat storage and added heat, this kind of passive component, goes up as a function of time. This crossover can happen depending on the model that you pick at different times, but it's a little bit kind of the emergence of the added heat pattern over time that we see that will kind of take over the pattern of redistribution, meaning, again, that the background circulation can dictate or kind of can explain what we will see in the future in terms of patterns of heat storage. Okay, so I'm going to sum it up and kind of, I was hoping to have kind of a few bits of time for question. So let me kind of wrap up, you know, what I talked about. First thing that we found was a relationship between the global heat storage and global carbon storage And so that was this figure over here, which shows that global heat uptake versus carbon uptake in the different observations and models scale linearly with one another. And I presented some kind of scaling that depended on the background carbon inventory and the buffer factor, kind of determine that relationship and the magnitude of that relationship. Then the second piece of the puzzle in that heat to carbon uptake or storage piece that we used was the fact that anthropogenic carbon is completely unaffected by a changing ocean circulation. That was shown in Mike Winton's paper. This is not our, this is nothing new. But the part that was interesting is that the pattern of added heat in which the circulation doesn't change is identical to the pattern of carbon storage. And so we use that similarity, that correlation, together with this kind of coupling between the heat and carbon storage to infer what a pattern of added heat would be in observations and in climate model, and look at the redistribution as a residual. As I said, over the historical period, the observed trends were dominated by redistribution. So the changing ocean circulation has been basically dictating how much thermosteric sea level rise we've seen, again, to first order. Bit of mixed bag in the CMIP5 models, but again, it depends which model you pick. The ones that are closer to the arms shows the same kind of split. If we look into the future, then it's pretty different. The passive uptake seems to dominate. That means that if all you need is the background ocean state to actually determine what the patterns of heat storage and thermosteric sea level rise will be, might make our life a bit easier. And again, we've been working with Emily Newson, who together we've been working on trying to find emergent constraint for those future warming patterns, and we can link them to the stratification. And that kind of makes sense when you think about it, because the stratification tells you it's a bit of a resistance to how much heat uptake you can get, but also quite important in terms of the carbon inventory and this kind of solubility picture. So it's temperature dependent. So we're hoping to take that one step further and find a way to kind of, again, extract some emergent constraint on what the patterns of heat storage and carbon storage might look like into the future. And I leave it at that and take questions or comments if there are any. Thank you very much.
Thank you very much, Laure. That was a fascinating talk, particularly for finishing on time, rather miraculous, as we've been interrupting you quite a bit. We've got Amanda is clapping. That's great. Do we have any questions from the group? Give it a minute. Sometimes people are stumbling.
Mm-hmm.
So since nobody else is jumping in, so presumably you've looked at what the implications are for this change for regional sea level change, right? Or do you need more information about the vertical distribution?
So definitely the vertical distribution is important, right? Because where you store heat does matter. So for the Atlantic, we find that about, on average, about half of the thermosteric sea level rise in the low to mid latitude is due to the changing ocean circulation. So that's roughly what we get.
That's more than one might have thought, I guess.
Indeed, right?
More than I thought.
Yeah, to be honest, me too. But again, in the future, that might change a fair bit because again, the added heat becomes more dominant and the redistribution becomes less.
Okay. One of the things that's kind of interesting to us, and I think maybe to Craig as well, so I mean Craig can jump in too, is what's happening in the southern oceans, where you're seeing uptake of heat, but the changes in stratification of things seem to be mediated more by changes in freshwater than the changes in temperature, which are going the other way. Right, so one would anticipate that something very different would be happening in the Southern Ocean. Do you see that? Can you diagnose that?
Yeah, it's a great question. So that's exactly what we're looking at when we're looking at those patterns of stratification. trying to pinpoint what's temperature driven versus what's salinity driven. But it looks like at the end of the day, as long as you know the stratification, it almost doesn't matter what sets it. This is still your resistance to heat uptake. And so there's still information, even though the stratification might be changing or was set by something different than just warming or fresh water. But that's definitely something we're looking into, and definitely a very interesting part.
Yeah, it's a really interesting problem. Perhaps one to think about is that the meltwater is not included in a lot of these Earth system model projections going forward. So,
oh, you mean the way Ben did it, right? So kind of adding an extra freshwater perturbation. Is that what you mean?
Yes. So we have a
yeah. So that's a great point. So that's a good point. Yeah, and that's definitely not included. Okay. Yeah. Sorry. So that if that was the point, definitely something left out.
We have a question from Brian. Do you think alpha will remain similar as you move to a much warmer ocean?
Oh yeah. So I'm trying to put a student to work on that because again, the scaling depends on the carbon inventory and the buffer factor, and so there is always the question of, would alpha remains the same and only depends on the background, or, would it change? And the question I'm very interested in is what happens if hopefully we get smarter and we stop emitting and, we try to reduce emission at some point, would alpha actually be controlled by the same, by the same mechanisms? And so great question. I don't know, but something we're looking into for sure.
A question from Max. Did you say at the end that the increase in future stratification in the RCP scenario is small enough to be corrected for in heat as a passive tracer?
Okay, so those changes in stratification are not necessarily small, but the background is so important and massive that it dominates over the redistribution, but they're still linked in a sense that, so okay, that might be a bit of a kind of overreach, but at the end of the day, when you start changing the stratification, it's kind of responding kind of a thermal wind balance. And so that will depend on the background you start with, and then we'll adjust based on those changes. So the changes are, get damped depending on if the stratification was strong to start with. And so they're going to be more strongly damped if you started with a strong stratification. So that will be kind of, regionally dependent. If you start with a strong background stratification, the changes are kind of damped quite quickly or more massively than if you don't, because it's easier to disturb a place where you don't have a strong stratification.
Yeah, sorry. One thing that I did not articulate earlier, which I was thinking about, it'd be interesting if you included meltwater within your scenarios, as that might impact the change in circulation, perhaps, in polar regions. Yeah,
absolutely. I mean, again, all the simulation we used were the ones in which, we had a fuller system model with everything, without having to do new runs, right? There were all runs of opportunities, but it would be very interesting to actually see the decomposition in different models. But also, I mean, it's not a selling point, but I hope people who are interested in that, who have CMIP6 Earth system models, I'm hoping many of you in the audience do, it's very easy to do what we've done. You just need to calculate global heat uptake to carbon uptake, take your pattern of anthropogenic carbon and just multiply it by that number, and you'll have the decomposition I showed. So it really takes almost no time, if you were interested.
Do we have any other questions from the group? Okie doke. So if we don't have any further, oh, we have a question from Natasha. Just to break things up, is there any chance you'd like to unmute, Natasha?
Yeah, sure. Hi, Laure. Thank you for a great talk. I mean, it's very interesting. And I have, looking at the ocean heat uptake, especially from the Zanna 2019 data set, and comparing to the World Ocean 2018. And we are finding a discrepancy between the two data sets, the trends and the magnitude in the upper versus the deeper parts of the ocean. Do you want to comment on that and say how you expect that that would affect the patterns that you showed? Thank you.
Yeah, no problem. Yeah, good question. So of course, so for those who don't know, Zanna et al. 2019 was a reconstruction using Green's function. So assuming a constant ocean circulation of heat uptake going back in time. So I'm not surprised that there are differences, right? Simply again, because we assume that the ocean circulation is constant. So that means that, you know, if you have regions in which, you know, warming is accelerated in some region because the changing ocean circulation, this is completely ignored in our reconstruction. And so I think we make that clear. It's a time independent, you know, circulation. So that's definitely one reason why the trends are different. The split between upper ocean and deep ocean, my guess, and that's a guess, we're trying to redo that with different Green's function, is that it's possible that the Green's function were estimated from echo, and that the ventilation between the upper ocean and deep ocean is just, you know, a little bit off. But again, you know, it's always hard to tell because the observations have their own, you know, say spread or errors because we have so few observations at depth. But yeah, great point. But I'm not surprised that they are different, right? So reconstruction, I would never claim it to be perfect, far from it. But I hope that gives you a hint of what might be the reason.
Okay, Dirk, thank you very much. Do we have any further questions, final comments? I don't think we do. If anyone does, please jump in. I'd just like to thank Laure again for a fascinating talk.
Thank you very much for having me.
I see.
Thanks a lot.
Thank you everyone for joining us. And thanks again, Laure, and I hope you all have a great rest of the day.
Thanks, you too. Thanks, Craig. Thanks, everyone.
Thank you.
Thank you.
Thanks.